The next thing you need to remember from Chem 20 is about intermolecular forces. Now, make sure that you keep these two terms straight. There's intramolecular forces that we learned in Chem 20, like covalent bonding and the bonds inside the molecule. That's not what we're talking about here. Intermolecular forces are the forces between molecules. So here we've got the three different intermolecular forces that you need to know: London forces, dipole forces, and hydrogen bonding. So you may want to even just start in your notes by putting a note somewhere to yourself, just as a reminder that we're talking about, for example, intermolecular forces. So not the bonds holding that water molecule together, but the bonds that maybe are bonding that water molecule to that water molecule. So it's the bonds, the attraction between those two separate molecules that we're talking about, and what type that is and what strength they are. So you maybe want to just make a little note to yourself next to intermolecular bonding, reminding that it's between molecules that we're talking about here, and maybe draw a little diagram if that helps you to remember. All right. Now, London forces are, you'll hopefully remember from Chem 20 that everything has London dispersion forces. They are basically momentary dipoles that work like this. So anytime you have an atom, so there's your nucleus, and we've got electrons cruising around. Let's say there's 4 electrons. Now, those electrons we tend to draw in these nice pretty orbits. The orbits are actually really, really messy. But at any one time, let's say that those 4 electrons, if we could stop time, maybe those 4 electrons would be spaced around that central, that nucleus like this. So you can see that there's 4 electrons on the left side of this and really none, or very kind of that one on the right. So if we were to stop time right then, this end would right here be slightly negative, and this side of that atom would be slightly positive, but only for that brief moment in time. Because if we were to unpause time, then all of a sudden, maybe in the next moment, the electrons look more like this, a little more neutrally spaced. A moment later, maybe it's over here, and now the right side is slightly negative, and the other side is slightly positive. So these are very, very fleeting moments of having a positive end and a negative end, and they change very, very rapidly. So it doesn't tend to stick around long, and so the strength of the attractions tends to be quite weak because they're so momentary. I think of this as kind of like junior high attraction. You're walking down the hall, you see a girl, you're like, oh, she's cute, or girls, he's cute, whatever it might be. But 10 seconds later, you see somebody else, and you're like, oh, but they're really cute. So these are very momentary. These don't last long at all, probably like most of your junior high relationships. They're quick attraction. Now I'm not attracted to you. I've moved on, kind of thing. Dipole forces are a little bit different. In these kind of attractions, these are permanent dipoles. So you remember in Chem 20, we looked at molecules that have, let's say, NH3, right? Ammonia. And you remember that there are bond dipoles. So in between the hydrogen and the nitrogen here, we know that that sharing of electrons is not equal. So in Chem 20, we would have drawn these in kind of like this. That there are these unequal sharing of electrons. So the electrons spend more time around the nitrogen always. Not just a temporary thing, but they're going to spend, it depends on the molecule, but let's say 70-80% of their time around nitrogen rather than hydrogen. That means that the nitrogen will always have a slightly negative charge, and each of these hydrogens will always have a slightly positive charge. because that is a permanent attraction and not a temporary one, these dipole-dipole moments are stronger. So this nitrogen will always have a negative charge. It's not going to suddenly flip at some point, which means because it's always negative, it can always be attracted to something else that's always positive, and that's a much stronger type of attraction. Okay. The last one is hydrogen bonding, and that the most common example for this would be in water, but ammonia also can do hydrogen bonding. It's anything that has an N, an O, or an F bonded directly to a hydrogen. So if you have an N to an H, an O to an H, or an F to an H, those are capable of what we would, they're basically a dipole-dipole bond, but because they're so strong of a dipole bond, we consider them their own thing, and they have what we would call hydrogen bonding. So in this case, same thing, that bond dipole is so strong that this is negative, these are positive, and this case just means that that has a stronger, that's an even stronger dipole than something else that might have a similar setup. So when water, for example, if we had a water molecule here, and we had another water molecule above it, like that, we would say, if we were to try to talk about this bonding, we would say that in between these, between the water molecules, we would definitely have London dispersion, because everything has London dispersion. We would have dipole-dipole, but because we also have an O attached to an H, we would have hydrogen bonding as well. So water is capable of all three types of intermolecular bonding. Some molecules will only have London dispersion. Remember, everything has London dispersion. But some molecules might have only two, right? They may have the dipoles, permanent dipoles, so they can do dipole-dipole, but they don't have an N, O, or F attached to an H, which means they won't be able to do hydrogen bonding. Those are going to be important if we go back to the notes when we look at this part here. And that's how these intermolecular forces affect these three things. So the first is the state of matter. The stronger the bonds between the molecules, the more dense the state of matter will be, which is why, for example, water is liquid at room temperature, because it has London dispersion, dipole-dipole, hydrogen bonds that hold the water molecules together. It would rather stay at a liquid state because those bonds are so strong. If you look at methane, for example, it doesn't have those stronger dipole-dipole and hydrogen bonds. So at room temperature, it's a gas. The molecule spreads out more because the attractions between the molecules aren't strong enough. It's also going to affect the boiling and melting points, and we're going to talk about that a lot in this unit as we go through it. But if you were to compare two molecules, let's say methane and water, because we were just talking about those, the water will have a higher boiling point, which is also why its state of matter is liquid, than methane, and that's why we can compare them. So we could not necessarily estimate exactly what those boiling or melting points are, but it gives us a really good way of saying, I know that the boiling point of that molecule will be higher than the boiling point of that molecule because of it has stronger intermolecular bonds. And then the last one that we'll use that for is solubility. And the general rule for solubility is like dissolves like. So the more similar two molecules are in terms of their intermolecular bonding, the higher the chance of them being soluble is. So for example, water, we've just mentioned, has all three types of intermolecular bonding. It's a very polar molecule. It likes to dissolve very polar things. So the more similar they are to each other, the better the chance of them being soluble. If you were to take something like water that's very polar and a non-polar molecule, they would not dissolve very well together. And that's why water and oil don't mix. water is very polar, and oil is very non-polar. And so because they're so different, those two things can't combine, and you get little water droplets floating on, or sorry, little oil droplets floating on water and things like that. You've probably seen situations and experiments like that in the past. So the last thing here is modeling kits. Now we won't be able to do much of this obviously because you're not here, but I just wanted to show you this. This is a form of modeling kit, and you may get exposed to these later on in other courses if you move on and do more chemistry. But the modeling kits are, and you hopefully have done some with them in Chem 20, but the modeling kits are essentially just balls or structures that allow us to represent atoms. Typically the color, in this case black, is carbon, whites are hydrogen, and reds are oxygen. So you may see these, even pictures of these on assignments or test questions or something like that. But I'll always provide a key so that you know what is what when you're looking at it. But that's it. We won't really get to do much of that because you're not here, but I wanted to point that out to you. So that covers the first page. And this is really all the review stuff from Chem 20 that you need to have. In the next one, we're going to jump into the new material for Chem 30.